All right, imagine this. You're at the airport. You're just about to board your flight. Maybe you found your window seat, got your headphones on, and boom, this thought pops into your head.
Yeah.
How does this, massive airplane with all the people, all the bags, the cargo, how does it actually stay balanced up in the air?
Yeah, I know what you mean.
Maybe you're not even at the airport. Maybe you're just fascinated by how these things work.
Yeah.
That feeling of, like, is it nose heavy? Is it tail heavy?
Right.
Well, it all comes down to this critical calculation, and that is the center of gravity, or CG. And that's what we're diving deep into today, how this crucial calculation is done for an airplane.
And for this deep dive, we've got Chapter 10 of the Weight and Balance Handbook.
Oh, yeah.
As our guide, this is, really the gold standard for understanding how an airplane's center of gravity, or CG, is determined. And we'll be exploring the tools and techniques they describe. You go from surprisingly simple math to these specialized flight computers.
Yeah, if you're listening to this and you're thinking about a career in aviation, you're an aviation enthusiast, or you just appreciate the incredible engineering behind flight, understanding CG is fundamental
Absolutely.
to safe and efficient aircraft operation. So what we're going to do is we're going to take what seems like complex calculations, break them down into understandable steps, and along the way, hopefully reveal some really interesting insights too.
Yeah, our exploration today, like you said, it's based on these excerpts from Chapter 10 of the Weight and Balance Handbook, and we do have some diagrams from the handbook
Oh, great.
showing typical airplane weight and balance data, different types of flight computers, and of course formulas and examples, to bring all of this to life.
That's fantastic. So our mission today is to unpack these methods, show you not just how these CG calculations are done in practice, but why. We want to go beyond just memorizing these formulas, but really understand, like, what is the principle behind this and why does this work? So what I found fascinating right off the bat, the handbook, emphasizes, I think, a great point, which is the simplicity of the math involved.
Yeah, they emphasize that almost all weight and balance problems involve, basic addition, subtraction, multiplication, and division.
Exactly.
And, it's tempting to think that something this, crucial, balancing an aircraft would involve really advanced math, but it's really rooted in these fundamental operations. It kind of makes the whole thing less daunting, doesn't it?
Absolutely.
Yeah.
It is, I don't know, it's kind of comforting to know
Yeah.
that some of the, core principles keeping these multi-ton machines balanced in the air come down to the math we learned in grade school.
Right.
So they start by looking at calculating the CG using, like, just a simple electronic calculator.
Yeah.
And they give us a great example here. They have figure 10, which shows the weight and balance data for a typical, this is a nose wheel airplane.
Right. Figure 10 too. Yeah, they give us some numbers to work with. So we've got 830 pounds on the right main landing gear, 836 pounds on the left main landing gear, and 340 pounds on the nose landing gear.
Yeah.
The arm, which is the horizontal distance, right,
Mm-hmm.
from our chosen reference point, is 128 inches for the main gears and 50 inches for the nose gear. The total weight of our hypothetical aircraft is 2,006 pounds. And then, importantly, they give us the distance between the main landing gear and the nose landing gear, which is noted as L.
Mm-hmm.
And that is negative 78 inches. Now, that negative sign there is key.
Oh, yes. And as the handbook clearly states, that's because the nose wheel is ahead of the main wheels.
Right.
So it's like in the opposite direction from, I guess, our main reference point.
Right, like on a number line.
Exactly. It's like if
Yeah,
you're measuring
something like
distance,
that.
if you're measuring to the left, it would be a negative number. So
Yeah.
to figure out the CG from these main wheel weighing points,
Right.
there's a formula.
The formula is CG equals nose wheel weight multiplied by the distance between main wheels and nose wheel, all divided by the total weight.
Right.
Or if we're using the abbreviations, CG equals FALW.
Okay, great. So if we plug in those numbers from our nose wheel airplane example,
Yeah.
that's going to be 340 pounds times negative 78 inches, all divided by 2,006 pounds. Punch that into a calculator. What do we get?
You should get negative 13.2. They even show the keystrokes.
Wow.
If you're using a very simple calculator,
Oh, wow.
it's 340 A78 plus minus 2006 minus 13.2.
That's really interesting. So the negative sign in this answer means that the center of gravity is actually 13.2 inches ahead of the main wheel weighing points.
Right.
Okay, so they move on and they introduce a really neat tool, and that is the E6B flight computer.
Yeah, it's a cool tool.
Yeah.
Yeah.
For those of you who haven't seen this, it looks kind of like a circular slide rule.
That's right.
Really an interesting piece of analog technology.
Yeah, the handbook points out that it doesn't have, or unlike a slide rule, the scales typically range from 1 to 10. The E6B's scales go from 10 to 100. And it's not designed for addition or subtraction, but it is incredibly versatile for multiplication and division. And the handbook says it's accurate enough for most weight and balance problems.
Okay. So they walk us through solving this exact same nose wheel airplane problem.
Yeah.
Using the E6B. I mean, isn't that kind of amazing that this mechanical device can do the same thing as a modern calculator?
It's so cool.
So how does it handle that multiplication? You know, the 340 times 78.
Yeah, so for 340 times 78, initially we're just going to work with the positive value, so 340 times 78. You place what's called the index, which is the 10 mark on the inner scale, and you place that opposite the 34 on the outer scale. Then you locate 78 on the inner scale, and you read the value on the outer scale directly opposite to it, and that should be about 26.5.
Okay.
Now, to get the actual magnitude of our answer, we need to do a quick estimation.
Okay.
300 times 80 is 24,000, right? So 340 times 78 is going to be in that ballpark. So that 26.5 represents about 26,500.
Got it. So that 26.5 on the E6B is actually 26,500.
Right.
In our calculation, then comes the division, 26,500 divided by 2006. How does the E6B handle that?
Okay, so for division, you place the 20 on the inner scale, and that represents our total weight of 2006. Now, we're kind of approximating here just because it's a slide rule. You place that 20 directly opposite the 26.5 on the outer scale, which was our moment, right, of 26,500. Then you find the index, which is the 10 mark, on the inner scale, and you read the value opposite it on the outer scale. That should give you about 13.2. And again, we can do a quick mental check. 20,000 divided by 2,000 is 10. So our result of about 13.2 for 26,500 divided by 2006 makes sense. And of course, just like when we did it with the calculator, because that arm of the nose wheel is negative, our CG is going to be negative 13.2 inches.
Amazing. It's pretty remarkable.
Yeah.
It's like this mechanical tool can get you the same precise answer.
Yeah, no, right?
Really speaks to the ingenuity of, I guess, those early flight aids. So they move on. They talk about a third way of calculating CG, and this is dedicated electronic flight computers.
Yeah.
These are like the handheld devices you see pilots using all the time in the cockpit.
Yeah. Figure 10-5 in the handbook shows one of those. They say, and this is, these computers are programmed to solve a whole range of flight problems, including, of course, weight and balance.
Right.
The advantage here, they say, is that they typically prompt you for the necessary data. So you don't even have to memorize the different formulas. You just punch in, the weights and the arms, and it does the calculations for you. It usually gives you running totals for the weight, for the moment, and of course, for that final CG.
Yeah, that sounds super convenient.
It is.
And it's got to, I would imagine, reduce potential errors.
Absolutely.
If you're up there in the cockpit, things are busy.
Yeah.
So while it's neat to see how to do this on the E6B, it sounds like those electronic flight computers, that's probably the workhorse.
Right.
Because it's so accurate and so fast. So the handbook then moves to, I think, this slightly more involved concept.
Yeah.
Which is determining CG in inches from the datum. So for those listening, the datum is essentially an imaginary vertical reference plane. They established this somewhere on the aircraft.
It's like your 0 point.
Yeah, it's like the 0 point from which all the longitudinal arm distances are measured.
Right.
And so to find the CG relative to this fixed datum, we often have to first calculate the CG relative to one of the landing gear weighing points, like we did earlier.
Right.
But then we got to kind of relate that position back to where the datum is.
Yeah.
So the handbook outlines 4 different scenarios.
Right.
And is based on whether the airplane is a nose wheel or tail wheel type, and also whether the datum is located ahead of or behind the main landing gear.
Right. That's important.
So let's break down 1 or 2 of these scenarios to really see how this datum comes into play. So first, let's look at a nose wheel airplane where the datum is located ahead of the main landing gear. So the handbook gives this example where the datum, which they denote as D, is 128 inches ahead of the main wheels. The nose wheel weight, F, is 340 pounds. The distance between the main and nose wheels, L, is 78 inches. And the total weight, W, is 2,006 pounds. And for this specific scenario, they give us the formula.
Right. And that formula is CG equals D, FALW.
Okay, so first step is to calculate the CG relative to the main wheels.
Right.
Which we already figured out.
We did.
That was 348, 2006 equals 13.2 inches.
Right.
and it was negative, meaning it's actually ahead of the main wheels.
Right.
So the datum is 128 inches ahead of the main wheels.
Right.
And we're going to subtract the 13.2
Correct.
from that.
Yes.
128, 13.2, and what does that give us?
That gives us 114.8 inches. So in this configuration, the CG is located 114.8 inches behind the datum.
Okay, so the datum is that fixed starting point, and we're measuring
Right.
the CG's location relative to that datum.
Exactly.
Okay, what about if we have a nose wheel airplane, but this time the datum is behind the main wheels? So they give us another example. A datum D is 75 inches behind the main wheels. The weights and distances are the same. What formula do we use here?
So the formula adjusts a little bit. It's CG equals Nash's D plus FALW. And again, we already know from our previous calculations that CG relative to the main wheels is 13.2 inches, and that's ahead of the main wheels. Now we just plug into our formula. Nash 75 plus 13.2, and that equals, Nash is 61.8 inches. And of course, the negative sign here means that the CG is 61.8 inches ahead of the datum.
Got it.
Yeah.
So it's all about that consistent reference point. Now, the handbook also talks about tailwheel airplanes,
Yes.
which of course have a different landing gear configuration.
Right.
So it's got the small wheel at the tail instead of at the nose.
Right.
So the formulas have to adapt to that.
Right, they do. So for a tailwheel airplane with the datum located ahead of the main wheels, they give us an example where the datum D is 7.5 inches ahead, the tailwheel weight R is 67 pounds, the distance L between the main and tail wheels is 222 inches, and the total weight W is 1,218 pounds. And the formula we use here is CG equals D plus RALW.
Okay, so first we got to calculate the CG relative to the main wheels.
Right, so that would be 67 times 222 divided by 1218, which gives us 12.2 inches. And because our tail wheel is, behind the main wheels, that 12.2 inches is also behind the main wheels. So then we add that datum distance, 7.5 plus 12.2, gives us 19.7 inches behind the datum.
Okay, so what happens when the datum is behind the main wheels?
Right, so they give us one more example for this section where the datum is, 80 inches behind the main wheels, and everything else is the same. The formula is CG equally managed D plus RALW, and we already know the CG relative to the main wheels is 12.2 inches behind them. So negative plus 12.2 equals negative 67.8 inches. So that means our CG is 67.8 inches ahead of the datum.
Wow, so you can really see how the type of landing gear and the datum's position can really impact how we calculate, but also interpret the CG relative to that fixed reference point. Now they move on and they talk about another, I think, fundamental way to determine CG.
Right.
And this is looking at the weights and the arms.
Yeah, the arms.
Like the distances from the datum of different components of the aircraft. So they give us, figure 10.6 is a great example. It's a table showing weight and arm specifications for that nose wheel airplane.
Right.
We've got the right main landing gear assembly weighing 830 pounds, and its arms 128 inches. The left main's 836 pounds, same arm, 128 inches. And then the nose gear assembly is 340 pounds, and it's got an arm of 50 inches.
Yeah.
So the process here is to calculate the moment for each of those weighing points. And a moment, for those who don't know, it's simply the weight of an item multiplied by its arm, the distance from the datum. Then you add up all those individual moments.
Right.
And then divide that total by the total weight of the aircraft, and that gives you the CG.
Exactly. So for the right main gear, our moment is 830 pounds times 128 inches equals 106,240 pound inches. For the left main gear, it's 836 pounds times 128 inches equals 107,008 pound inches. And for the nose gear, it's 340 pounds times 50 inches equals 17,000 pound inches.
Okay.
If we add up those three moments, our total moment's 230,248 pound inches. Now we know from before that our total weight is 2,006 pounds. So CG is total moment divided by total weight. 230,248 divided by 2006 equals 114.8 inches from the datum.
Wow. And that matches one of our previous calculations.
It does.
So you know what? That really underscores
It does.
the accuracy of this, because we're arriving at that same answer using a different method. Then they introduce this concept of moment indexes.
Right.
What is the idea behind these indexes?
Okay, so a moment index, they show this in figure 10.7. A moment index is basically a moment that's been divided by a constant reduction factor. In this case, the reduction factor is 100. So they're basically just working with smaller, more manageable numbers.
Right.
So it kind of makes it easier, to work with these numbers and less prone to errors, I guess, if you're doing it manually.
Right.
The overall process is still the same.
Okay.
You sum all the individual weights, sum all the individual moment indexes, then you divide that total moment index by the total weight, and finally you multiply by the reduction factor,
Okay.
which was 100 in this case, to get the CG.
All right, so using the data from figure 10.7, we have the same weights,
Right.
but now we're given their moment indexes. So for the right main, it's 1,062.4.
Right.
And that's indeed 106,240 divided by 100. For the left main, it's 23 0.1. And for the nose, it's 170. The total weight's still the same, 2,006 pounds. And the sum of these moment indexes is 2,302.5.
Right. So then you divide that total moment index, 2,302.5, by the total weight, 2,006. And that gives you about 1.148. And then you multiply that by your reduction factor, which is 100, and you get, look at that, 114.8 inches.
Yeah, exactly.
That's the answer.
It's the same CG that we found with the, more direct calculation.
Right.
It's just, slightly different way of dealing with the numbers. Now, for those who are really, into the aviation world, they often express the CG location not just as inches from the datum, but also as a percentage of the mean aerodynamic chord, or MACE.
Right.
So what is the MACE, and how do we actually go about calculating the CG as a percentage of the MP?
Right. So the mean aerodynamic chord of MACE, it's not, literally just the average width of the wing.
Right.
It's more like a representative chord line along the wing where we consider the aerodynamic forces to be acting.
Okay.
So expressing the CG as a percentage of MACE, it gives us another way to define the aircraft's balance. It lets us, compare balance characteristics of different aircraft.
Okay.
Regardless of the wing's, shape and size.
Sure.
So they give us an example. A loaded CG is located 42.47 inches aft. So that means behind the datum. And they say the MAC length for this aircraft is 61.6 inches. And the leading edge of the MA, which is abbreviated LAMAC, is located at station 20.1 inches from the datum.
So first step would be to figure out the distance between our actual CG location and the leading edge, this MAC.
Exactly. So it's a simple subtraction.
Okay.
42.47 inches minus 20.1 inches, and that gives us 22.37 inches. So that tells us our CG is 22.37 inches aft of the leading edge of the MAs. Now, to find that CG as a percentage of the total MAC length, we use the formula, and that formula is the distance between the CG and LEMAC divided by the MTI length, all times 100. In this case, that would be 22.37 divided by 61.6 times 100, which gives us approximately 36.3%.
Okay.
So we can say the CG is located at 36.3% of the mean aerodynamic chord.
Interesting. So it's more of a relative measure then of where the CG is within
Right, it is.
the wing's kind of aerodynamic sweet spot. Now, they also touch on helicopters.
Yeah.
Which, as you can imagine, have their own weight and balance considerations.
They do.
And that includes this really critical aspect of lateral CG.
Right, lateral CG. So with helicopters, you need to figure out not just the longitudinal CG, which is the balance along the fuselage, but also the lateral CG. That's the balance side to side.
Right.
That's measured relative to a vertical reference plane called the butt line 0, or BL0, which basically runs lengthwise through the center of the helicopter. And if something is left of BL0, it's negative. If it's right, it's positive. Figure 10-8 in the handbook has a great illustration of this.
So looking at that data, they give us various components and their weights and also their lateral arms.
Right, their lateral arms.
So like the pilot seat might be offset to one side.
Right.
The fuel tank might be offset to the other side.
Right.
So to calculate the lateral CG, we need to figure out the lateral offset moment.
Exactly, yeah. You multiply the weight by the lateral arm.
Right.
And here, it's super important to pay attention to those signs plus and minus, because that tells us if the weight is on the right or the left of that BL0. So in figure 10-8, they calculate these lateral offset moments for the empty weight of the helicopter, the pilot, a passenger, and the fuel. And then once you have all those individual moments, you add them up. And then to get that lateral CG, you just divide the total sum of those moments by the total weight of the helicopter. So in that example, they end up with negative 1,705 pound-inches as their sum of lateral moments. And the total weight of the helicopter was 200 and 203 pounds. So that gives us a lateral CG of about 0.77 inches.
Okay.
And the negative value tells us that the helicopter CG is 0.77 inches to the left of that butt line 0.
So it's the same principle as we saw with longitudinal CG. It's just that we're applying it now to the lateral axis.
That's right.
So now the handbook moves to, I think, some really practical,
Yeah, they get into some real-world stuff.
real-world scenarios.
Right.
What happens when we shift weight in the aircraft?
Right.
Maybe passengers move around, cargo gets shifted. what happens to that CG?
So, these are the things pilots and ground crews have to think about all the time. So let's say you have 50 pounds of baggage, and we move it from an aft compartment, that's the rear compartment, at station 246 to a forward compartment at 118.
Right.
And let's say the total weight of the airplane is 400 and 709 pounds.
Okay.
Now, the handbook gives us a formula to calculate the change in center of gravity,
Okay.
or delta CG, and it's weight shifted, distance weight is shifted, total weight.
So first we got to figure out the distance that the baggage was moved.
Right, that's easy. 246 minus 118 equals 128 inches.
Okay.
Now we just plug into our formula. 50 pounds times 128 inches divided by 400 and 709 pounds, which gives us about 1.36 inches.
Okay.
So because that weight was moved forward, our CG also shifts forward by 1.36 inches.
Okay.
Now, the neat thing is you can use this formula in a reverse.
Okay.
Let's say you know how much you want to change the CG, right? You want to move the CG forward by, say, exactly 2 inches by shifting weight between those same stations, 246 and 118. How much weight do we have to move? Well, the formula becomes weight shifted equals total weight times delta CG divided by distance. Weight is shifted. So we plug in our numbers. 400 and 709 pounds times 2 inches divided by 128 inches.
Okay.
And that's about 73.6 pounds.
Wow, that's really like practical information there.
It is.
For figuring out how to keep the aircraft within those safe limits.
Right.
What if you know how much weight you can shift
Uh-huh.
and you know how much you want to change the CG, but you need to figure out how far to move the weight?
Yeah, the handbook talks about that too. Let's say you have a 56-pound battery and you want to move it to shift the CG aft, backwards by 1.5 inches.
Okay.
And the airplane weighs 426 pounds. The formula here to figure out the distances. Distance weight is shifted equals total weight xEG, weight shifted. So for our battery, that would be 426 pounds times 1.5 inches divided by 56 pounds. And that works out to about 107.8 inches. So we'd have to move that battery 107.8 inches aft to get that 1.5-inch change in CG.
Really practical applications of the CG principles.
Yeah, it is.
Now, they give a scenario where you have to figure out the total weight of the aircraft
Yeah.
based on knowing a weight shift and the resulting change in CG.
Right. So let's say moving 500 pounds of cargo 96 inches forward results in a 2-inch shift in CG.
Okay.
How much does the airplane weigh in total? The formula here is total weight equals weight shifted x, distance weight is shifted, ICG. So we plug in our numbers. 500 pounds x, 96 inches, 2 inches. And that gives us a total weight of, get this, 24,000 pounds.
Oh, wow. That's a big plane
Yeah, it is.
compared to what we were looking at before. Now, finally, they talk about you calculate the CG and it falls outside of the limits.
Yeah, that happens.
So you need to add what's called ballast.
Right.
And ballast is just extra weight that you put in a specific spot
Yeah, it's to adjust the CG.
to bring that CG back in.
Right.
So they give an example.
Yeah.
An airplane has an empty weight of 1,876 pounds, and its current CG is at plus 32.2 inches.
Okay.
But the forward limit for this aircraft is plus 33 inches.
Right.
So the CG is actually a little bit too far back. It's 0.8 inches
Right.
after that limit.
Right. Uh-huh.
And let's say we want to add ballast at station 228 inches to correct this.
Okay.
So the formula for calculating that ballast weight is ballast weight equals aircraft empty weight x, distance out of limits, distance between ballast location and desired CG.
Right.
So first we got to find the distance between where we want to put the ballast,
Yes.
228 inches,
Uh-huh.
and our desired CG location, which is that forward limit of plus 33 inches. So 228, 33 is 195 inches. Now we can plug in.
Right.
So 1,876 pounds times 0.8 inches divided by 195 inches gives us, let's see, about 7.7 pounds.
Right.
So we'd have to add 7.7 pounds of ballast at station 228 to move the CG up to that plus 33-inch limit. So I think that pretty much covers it, doesn't it?
I think so, yeah.
The methods.
We went through a lot.
The formulas, the practical applications for determining and adjusting an aircraft's CG.
Absolutely.
So in summary, what we did today was we, looked at the fundamental principles
Yeah.
of calculating CG. And we saw that it's actually, fairly simple math combined with some specialized tools.
Right, yeah.
You got the E6B, you got those modern flight computers.
Mm-hmm.
And all of that plays a critical role in making sure planes fly safe and efficiently.
Mm-hmm.
We learned about the datum,
The dare.
calculating the CG as a percentage of the MAC.
Right.
We even looked at, shifting weights around, how to add ballast, and you should have a much deeper appreciation now
I hope so.
for the, I think, the precision involved in this calculation.
It's critical calculation.
It really is. So for all of you listeners out there, we hope that this exploration, satisfied your curiosity about this critical